Okay, I think we'll get started. So today we're going to talk about another group theory aspect, but this also involves homotopy theory, some topology. We're going to largely just look at examples here and not get too deep on monodromy theory. But we're going to look at the monodromy group for these Blaschke products, these finite Blaschke products. Okay, so this is based on the set of critical points, and these are going to be key points for the Blaschke function or Blaschke product, because these are going to be branch points through which we'll draw some branch cuts and be able to take paths around our Blaschke function going on to different Riemann sheets. And for an nth order or an nth degree Blaschke product, we should have n branches or n Riemann sheets. And when we take paths, circular paths through these, we'll basically be permuting through these Riemann sheets, and so the monodromy group will be either the set of permutations on n Riemann sheets, so the Sn group, or some subset of the Sn group. Okay, so let's just remind ourselves here now. If we take the inverse of the Blaschke product, the preimage will have n. For a generic point, we'll have n will be on n branches, except for the branch points, and we're going to define the first branch as the one in which the preimage of 0 is 0, and then the preimage of 0 is something else for all of the other branches in the set. Okay, so if we have a Blaschke function of this type, then again the preimage is 0, and then z1, z2 up through however many zeros we have. Okay, let's work into some examples. Again, we're not getting super deep in the mathematics of this, just some working examples is what we want to accomplish here. So let's define our Blaschke product as W here, and so we're going to be translating from the z-plane to the w-plane when we apply the Blaschke product, and then when we look at the preimage or B inverse, then we'll be coming back to the z-plane. Okay, so let's take the example here of a second degree Blaschke product with zeros at 0 and at 1/2. So we've seen this function before, but our zeros here are at 0 and 1/2. Now we're going to take the derivative of this function, which is doable, and so you can pause the video and work this out, or just follow along here. Here's the video. We're going to set that equal to 0, and we're going to get a critical point. Now, one of the fundamental properties of the Blaschke product is that we should expect n-1 critical points. Now, sometimes those are degenerate critical points, but here we have an n equals 2, so we expect one critical point inside the disk. There's another critical point outside the disk, but we're worried only about the interior and the unit circle, interior of the disk and the unit circle. Okay, well, let's invert this function. So basically, we're going to solve W equals this Blaschke product for z. Okay, and that's going to give us our two branches here. And so basically, we're inverting this. So you can go ahead and try to algebraically just solve for z, get z explicit, and we get fairly messy, but not too bad. We get this term. So let's just double check on this. So we're claiming that we want G1 to be the branch in which the 0 is 0. So let's check that. So if we stick in 0 for W here, we're going to get, in this case, we're going to get 1/4 1 minus, then these all go to 0, square root of 1, and that does indeed equal 0, so that's the right branch for that one. let's just confirm this is a different branch. So this should give us our 1/2 because we know the zeros are 0 and 1/2. So if we stick in 0 here, then we get 1 plus 1. So we get 1/4 of 2, which is 1/2. And so we recover our 2 zeros on each of the 2 different branches, G1 and G2. Okay, so now comes the homotopy here. We're going to consider all possible paths in the W plane that form a loop from 0 to 0. Okay, so how we do this is we find the, so we stick this into, so this is our, we solved this in the Z plane. This is the critical value in the Z plane. So we want that in the W plane. So we're going to take B of this value, and here is this value here in the Z plane, and that's going to end up here in the W plane. So it just happens it's a little bit negative and real. So you could check that out. You just plug this into here. Then we make a branch cut from here. We draw a chord across this unit circle, or this disk, and this represents our branch cut from the critical point to point alpha here, and a critical point, the critical point to the point beta here on the unit circle. Okay, so that's our branch cut. So as we pass across that cut, we're going to be moving from one Riemann sheet to another. We label this is the alpha cut and the beta cut here. Now, we take the inverse image of this branch point. And so notice beta is going to have 2 points, right? Because it's a degree 2, in this case, this is a degree 2 Blaschke product. So there should be 2 points on the unit circle that map to beta, and 2 points on the unit circle that map to alpha. And we then create, so this branch cut would be this one, and this branch cut right here would be this one. So now we're going to traverse, let's take a path. We have 2 choices here of paths, of simple paths. We can go around and back without encircling the critical point. That'll be the green path here, and then the blue path will be going around the critical point. So let's do the green path first. So as we traverse the green path, we go here, we cross the branch cut this way, the alpha branch cut this way, come back and cross the alpha branch cut the other way. So if we think about a Riemann sheet, we've moved up onto the other Riemann sheet, and then we've come back down. So we're back on our original Riemann sheet. And so when we come back to here, let's traverse this in the in this plane. So as I traverse, I come around, I cross alpha, and then I cross back. So these are going in this direction. Cross alpha and cross back. And I'll end up then back at this 0. So as I circle in this plane, the W plane, I end up back at 0. I could either be here or here, right? For the green, I end up back at this 0. Okay. Now, same would have happened over here. Let me do one in purple here. If I go around like this, right now I cross the beta line. So that would have been the same as doing something like that. I cross the beta cut and come back on the beta cut. End up on the same point. But a little different here for the blue curve. The blue loop, we're going to go around this critical point. And so I'm going to go up through the alpha cut onto one Riemann sheet, then I'm going to come back on the beta cut. So that'll get me onto a different Riemann sheet. So if I go up on the alpha, here I am, I've come across an alpha. Now, the next thing I do is cross a beta. So I can't come back this way or I'd cross the alpha. So I cross the beta and I cross into here, and we end up on this point. So this loop becomes this open line here in the Z plane. Now, if I were to go around again, if I go around again, now I'm sitting here, I go alpha, beta. So in this case, I wouldn't cross back this way. I would cross this way because here's my alpha, here's my beta, and I would complete that loop. So if we encircle twice, we walk from 0 to 1/2 back to 0 again. So what we do then is we look at these different paths, the green path and the blue path, and we see what kind of group that forms, and so that'll form a group, and that group is called the monodromy group. So what does this do? Well, the green path takes us from G1 to G1. Now, we should confirm that it also takes us from G2 to G2. So I would do something, I would do something like this, follow this, and I would cross an alpha and I would come back, and I end up back where I started. So that confirms that, in addition, this leaves this alone. It also leaves G2 alone. So this is the identity. So the green, G is for green here. So the green path is the identity. The blue path, we'll call that gamma blue. What does that do? That changed us from Riemann sheet 1 to Riemann sheet 2. So from branch 1 to branch 2. So that is going to take G1 to G2, and it's also going to take G2 to G1. So we get two group members. Now, should we be looking for more? Because you might need to go around more, take more paths. Pretty simple here that we think we've got all the paths. But one thing we should consider then is this should allow us to sample all of the permutations of the Riemann sheet. So this is a permutation of two things. So it's the S2 group, and the S2 group has only two elements. And they are indeed the identity, and then flip-flopping the permutation of 1 and 2. So 1 goes to 2, 2 goes to 1. And so indeed we recover the S2 group is the monodromy group. Okay, let's take a little bit of an aside here. We won't work through this in full detail, but we run into a bit of trouble when we have a Blaschke function like this. So this is normalized in the sense that Blaschke of 0 is 0 and Blaschke of 1 is 1, but it's not normalized to having a degree 1 or a 0 of order 1 at 0. It's actually a 0 of order 2, which unfortunately puts the critical point at the 0 as well. And we want to make these loops from the zeros. Technically, you wouldn't have to, but you generally want to do the loops from the zeros. So we'll do something we did in a previous video. We'll just kind of remind ourselves of that and quickly just talk about what happens here. So we saw in another video that if we use a special combination of compositing a Mobius transformation, the Blaschke function, and then a Mobius transformation, we can split that out and get a first order 0 at z equals 0. And the choice then, we can arbitrarily choose, if you recall that other video, we can arbitrarily choose a point, so we'll often choose 1/2. It's a good point to choose. So then 1/2 squared is going to be 1/4. So if we plug 1/2 into the Blaschke, that's going to be 1/4. And so if we do a Mobius transformation where our parameter is 1/2, then take the Blaschke product of that, and then do a Mobius transformation where our value is 1/4, then that will do what we need it to do. And so when you do that, you get this function, which indeed has a first order 0 at 0. Then we could find the critical point. The critical point is at 1/2. So we've defined this A as this new Blaschke product. So now we have recovered sort of what we had over here. We've got A taking us to the W plane, and then inverse A back to the z-plane. So I won't go through the homotopy group on, or the monodromy group on this. Instead, we'll just see that we've sort of made it into this form now. So you do have to do a little bit of pre-work if you've got a second order zero sitting there. Okay, well, let's do a little bit harder example, and this one's going to involve some algebra, that messy algebra that we won't go through. I'll take you over to the computer just to see it on Mathematica, and then plot for real, because just hand drawing these plots makes it a little bit difficult as well. So let's try a third order or a third degree Blaschke product. So our zeros here are going to be at z equals 0, z equals 1/2, and z equals I over 1/4. Now this isn't exactly a normalized, the phase is off, but you don't have to be working with normalized, strictly normalized Blaschke products as long as you're first order at 0. So with this, we can find the critical points, and we expect 2, and there are 2, and these are distinct. So we have distinct zeros, we have distinct critical points. So we should anticipate now, kind of predicting ahead, we should anticipate that we should get the full S3 group, which has 6 elements. If you have some convergence of the zeros or the critical points, then sometimes you just get a subset of the permutation group. Okay, so let's take these critical points and get their values when we stick them back into the Blaschke product. So that's going to be these two. And unfortunately, these are both very small and they're close together. So I'm going to exaggerate the drawing a little bit. We'll see it on the computer. The 2 points are pretty close to each other when you look at the whole disk. Then what we're going to do, and this is kind of interesting result here too, we're going to now look at the inverse image of these critical points. So we're going to actually need this. We're going to have our, of course, we're going to recover our 2 critical points up here, but we get then the critical points on a different branch. And interestingly, we get these repeated and then a new point here. So we have sort of 4 critical points here when we come back to the z-plane. So we have the inverse image of those points, and we're going to need those actually to figure out how to draw our curves. Or what, not how to draw curves, but when we draw a curve, what do they result in? Okay, so let's start to plot these. So we're going to have our w-plane over here, and our z-plane over here. So these 2 critical points right here, close together, I'm exaggerating them now. So here's one, and here's one. I've spread them apart so that we can draw through here. And we'll kind of walk through each of these curves. So we're going to start with this green curve. And so we've drawn our chord here that goes through these 2 points and through. So we've got 3 branch cuts here. We've got this cut, the beta cut, the alpha cut, and then the in-between cut. And so when we transform back, if we go in between in the w-plane, we have to go in between in the z-plane. If we go on the beta side, we got to go on the beta side, etc. Okay, so let's start. We're going to start at 0, and we're going to just go around the beta line and come back. So now in this z-plane, I have to find a beta line, and I'm going to go around and come back. And so we see that if we start here, we get this. If we start here, we get this. And if we start here, we get this. I have to do that. Okay. And so in this case, we end up back where we started. And so the green curve is the identity. So we should always be able to find an identity, and usually that's the one where we don't circle. I think it always is the one where we don't circle the critical point. Okay, so that's the green one. I'm going to try to erase these, otherwise it gets too much on here. Okay, So let's do the blue curve now. So the blue curve is going to go around, and we'll go around in this direction. So we'll go through the through branch line, then branch cut, and then we'll come back on a beta branch cut. So let's see if I can do this here. So I'm going to go through and back on the beta line. So I end up here, and we'll call this branch 2, and this 3, and this 1. Branch 1 is always the one with the 0 is 0. Okay, so what does it do? It takes G1 to G3. So let's try 2 now. So I'm going to start at 2. I got to go through and a beta cut. So I take G2 to G2. I went through the through cut and then back the beta cut, G2 to G2. And now I'm going to take G3. So G3 is going to go through and then through a beta cut. And so now I end up back at G1. So what does this do? Well, this takes 1 to 3, 3 to 1, and it leaves 2 alone. So it's a permuting 2 of the spots in this 3 spots system. Okay, so that's that curve. Let's erase this. And let's take black curve. So the black curve, let's go ahead and go this way. We'll go through the middle branch cut, or the in-between cut, and then come back on an alpha cut. So I'm going to go through the in-between cut and back on the alpha cut. So that means for the black, we'll call that gamma K, K for black instead of B here. I'm going to take 1 to 2. Okay. Then let's try 2. I got to go through a cut and then through an alpha. Okay. So I have to go through the through cut, or the in-between cut, and then the alpha. So that's going to take us from 2, let's see, the K cut. That's going to take us from 2 back to 1. And then let's look at the 3 cut. I go through and then back in alpha, and that takes me around. And so that stays the same. So what is that one? That is another pair permutation, permuting 1 and 2 and leaving 3 alone. Now let's do one last cut. So let's start and let's go around all of the critical points, okay, or both of the critical points. So let's try to do that. I'm going to erase this. So let's give a direction to this. I'll go around a beta cut and then come back on an alpha cut. Let's see, is that what I want to do? No, let's go, yeah, let's go this way. We have our choice of going around. We'll see, we would get a different answer, but they're going to be in the group setting, you can get one from the other. Okay, so I think we want to go alpha, then beta. Yeah, so we're gonna do an alpha cut, then a beta cut. So that's going to take 1 to 2. So P is for purple here. So we're going to take 1 to 2. Now what's 2 going to do? That's going to do an alpha cut and then a beta cut. So that's going to take 2 to 3. And then finally I got to go around this. I can't go through, I got to go around, and alpha cut and a beta cut. So that's going to take 3 to 1. So we're going to get just the 1 goes to 2, 2 goes to 3, 3 goes to 1. So we're going to get the cyclic, or the cyclic permutation there. Okay, so is this the S3 group? Well, we didn't get 6 elements, but we got enough to generate the group. So the group is obtained by doing all lines. So we can go around, many times. We can go in either direction. We could do some crazy, crisscross and then around like this. And these are all going to end up being products or compositions of these permutations. And the identity, the single permute, and the cyclic permutation are enough to generate the S3 group. So we actually picked up one extra that we didn't need, but we did pick up the generators, the necessary generators for the S3 group. So it indeed is the S3 group. Pretty interesting stuff, fun stuff. It gets a little bit hairy when you start to get high order high degree Blaschke products. You really need to probably have Mathematica or write a Python code to really see things, because it gets pretty tricky to draw. But certainly very interesting, this connection to group theory in this way in terms of the monodromy group. So as promised, let's go over to the computer, just very quickly go through this. I know I'll be using Mathematica here, and that's not something that you might have, but then I'll be using Python to plot this, so that is something that you certainly can have. Python is free, so you can play around with that as well. Okay, so I'm going to switch over to the computer, and let's go ahead and look at that. All right, let's do the Mathematica first. So I'm going to minimize that. All right, so I've defined my Blaschke product here, and we can see it's a little bit out of order here, but we can see this is indeed what we were looking at, that last Blaschke product. Now I'm going to take the derivative and simplify this, and notice we're going to look for 0. So we'd want this numerator, and we look at the numerator, and we see that it is 4th order. So we expect 4 solutions to this by the fundamental theorem of algebra. And so indeed we do get 4, but as was always the case, 2 of them are going to be inside the disk, and 2 of them are going to be outside the disk. So we always have n minus 1 critical points. And so this is a degree 3. So we have just 2 critical points that are in the disk. And we can see those right here. These are the first 2 right there. So those are the first 2. So then what we do is we take each one of these and put those into the Blaschke product. And so here's those values I had on the board, both very small, so they're going to be very close to 0. And when we plot these, they're going to be almost on top of each other. But the computer doesn't care. Okay, so now let's invert this now and stick in these numbers. So we're going to invert this. Actually, let me do this here. So you can see quite a big mess to get those branches, although it's possible with Mathematica. So here are the branches, the 3 branches that we expect for this. So we can kind of see them start here. Here's 1, here's 2, here's 3. Huge mess, right? But let's plug in the critical points on those branches, and we see we recover these critical points. So here's this, right? And I don't actually know why this is the case. I can't give you. I wish I could give you like a intuitive insight into that, but we get this repeated, and then we get our second sort of ghost critical point as well that we need to draw on the graph. And likewise here. So we recover, we get to the repeat is the critical point that we got from above, and then here's its partner on a different sheet. Okay, so now I want to look at the, so just wrote a Python program to plot these. So let's look over here in the W plane. So looking here, here are the two critical points very close together. So we're going to be making circles through these, and then we have alpha and beta labeled, and they're going to translate over here. So basically what happens is we get a transfer of back of this line, and we get 3 branches. And the branches here are in green, blue, and red. So we kind of see this structure, even with higher order groups. We get these curves through like this. So alpha beta line, and then an alpha alpha and a beta beta. Now how you draw them is kind of difficult. It's really nice to be able to write a program that will actually transform this back, because if you're just trying to eyeball it, you can get on the wrong side of these zeros and stuff very easily. It's difficult to just eyeball this inverse image. So it is nice to be able to have the computer give you the inverse image. But it's going to generally be in this kind of a structure, and you can kind of think of this as a line continuing through here. Has a lot of numerical instability by that critical point. Okay, now it does look too like this line is going, yeah, sorry, it actually is. So these diamonds are those sort of ghost critical images. So it does include those as well. And they'll be on that curve all the time. Okay, so this is looking pretty close to what I had on the board there. Sort of had this diagonal line here, and then we were making loops through, and they were making the various loops through these points here. So if I go through here on this point, then I have to be going either here, so here, here, or here. Right? Those are the in-between cuts. And then if I cross a alpha, then I have to be crossing either here, here, or here. Those are the alpha cuts. And then likewise for beta, here, here, or here. Those are the beta cuts. Okay, so this is that. Maybe a challenge for you if you're good at getting Python to work. See if you can code up for a different third order Blaschke product, and then see if you can code up for like in a general order and try to get a pretty crazy picture over here of like a 4th or 5th order Blaschke product, and working out these points and these curves, and then see if you can figure out the homotopy or the monodromy group. Now it's going to get big in a hurry because it's following the permutation group, which basically explodes like a factorial. So it's going to be difficult to get by hand get high order Blaschke products. All right, so that's it. Just a very light touching on the monodromy group. Beautiful theory in analytical or in analytic functions. So if you found that interesting, I encourage you to learn a little bit more about monodromy outside the context of Blaschke products. Also, the monodromy group is connected very much to homotopy theory, which is a pretty interesting area of topology. So that's pretty neat. And so a lot of different jumping off points here for you if you're interested in some of this stuff.